Welcome to a brief introduction to nucleophilic substitution reactions. During this discussion, we will be looking at the SN1 and SN2 reaction mechanisms and what sort of factors will influence a reaction to run by one of these two mechanisms. But before we do that, let's discuss the basic components of any nucleophilic substitution reaction so that we can define them and then use those definitions in our discussion. First, there's the nucleophile. A nucleophile can be defined as an electron-rich species which easily donates an electron pair to form a new bond heterogenically. So nucleophiles are characterized by dense regions of negative charge and the presence of lone pair electrons which are easily given up to form a new bond. So in this sense, a nucleophile acts like a Lewis base. The alter ego to the nucleophile is an electrophile. And these would be defined as electron-deficient species, which easily accept electrons to form the new chemical bond heterogenically. So electrophiles are going to be characterized by regions of dense positive charge, and in some cases, an incomplete octet of electrons. So electrophiles are very willing to accept acting as Lewis acids. And finally, because we're talking about substitution reactions, we have to have a leaving group as well. That is to say that if we add the nucleophile, we have to lose the leaving group. Otherwise, it's not technically defined as a substitution reaction. So a leaving group would be any substituent on a molecule which easily is removed by the withdrawal of its bonding electrons to form a separate stable species. So leaving groups would be characterized by any type of group which will tolerate the acceptance of these electrons and the formation of a negative charge within that particular group as it is departing from the rest of the molecule. So now that we've defined these players in the game, let's take a look at the two major classes of nucleophilic substitution reactions and see how these different components behave in each of the two mechanisms. Let's begin now by considering the SN1 reaction. In the depiction on this slide, you'll notice the nucleophile in green. This is the entity which will be donating electrons to form the new bond. The leaving group is depicted in pink, and the electrophilic carbon would be the carbon at the center of our T-butyl group. In this case, it looks like a T-butyl halide. You'll also notice that I've labeled the entire molecule which is going to be attacked as the substrate. This is typically how we refer to the molecule which will undergo nucleophilic attack during the reaction. So let's say that we're dealing with a T-butyl halide here. The entire T-butyl halide would be the substrate for my nucleophilic substitution reaction. As the SN1 reaction initiates, the leaving group departs from the substrate, and in doing so it creates a stable intermediate. So if we look at the energy diagram for this reaction, on the reaction coordinate there's going to be a local minimum which corresponds to the formation of a stable intermediate carbocation. Now let's watch that take place. You notice that the leaving group has departed, leaving us with a T-butyl cation. And this T-butyl cation is a stable intermediate. It's not long, however, before this stable intermediate is then attacked by the nucleophile. And in this step of the reaction, we reach the more stable final product. So the SN1 reaction occurs in two different isolated steps. First, departure of the leaving group to form the intermediate carbocation, and second, the nucleophilic attack of that carbocation to form the final product. What's particularly interesting about an SN1 reaction mechanism is that although I have shown the nucleophile attacking from the opposite side of the substrate, this is not necessarily going to have to be this way. If instead, my leaving group departs and the nucleophile then attacks from the same side of the substrate, we have a different type of product depending upon the stereochemistry of the starting material. Now in the case of a T-butyl halide, this won't have any consequence whatsoever on the product. But if we were starting with a chiral product, notice that at this point we would have an inversion of symmetry around about half, or in fact exactly half, of the products formed. Therefore, one of the consequences of the SN1 reaction is that there is a complete loss of stereochemistry. So some factors that favor this particular type of reaction would include use of weak nucleophiles. The weaker a nucleophile is, the less likely it is to attack before the departure of the leaving group, forming the stable intermediate. More substituted substrates favor this mechanism because hyperconjugation from alkyl groups will stabilize the carbocation intermediate. Better leaving groups on the substrate also favor the SN1 reaction because the leaving group is more likely to depart before nucleophilic attack occurs, as is the definition of an SN1 reaction. And additionally, the solvent choice will be important, but that's also going to depend somewhat upon the identity of the nucleophile, substrate, and leaving groups. And therefore, it's difficult to specifically say that a polar or nonpolar, that a polar protic or polar aprotic solvent would be best. This is going to depend upon the circumstances of the reaction. Now let's move on to the SN2 reaction mechanism. In this case, I've changed just a few things about the reaction that we have depicted. The first is I have altered the nucleophile to make it a hydroxide ion. This is a much better nucleophile than, for example, a halide ion, which may have been what we depicted in the previous slide. The other important change is we switched from a T-butyl halide to a methyl halide as our substrate. This is because in order to proceed through the SN1 reaction, a methyl halide would have to form methyl cation, which is a very, very unstable intermediate. So this particular substrate is much more likely to hold on to its leaving group until it is attacked by the nucleophile. So here we've identified our nucleophile as the hydroxide, our electrophile as the carbon on the methyl halide, and our leaving group as the halogen on the methyl halide. Let's begin the SN2 reaction mechanism and see how this proceeds. You'll notice that the nucleophile first attacks, and the leaving group has not yet completely departed from the substrate. This means that we form a single transition state rather than a stable intermediate. So the consequence of this is that our reaction coordinate diagram will not have a local minimum as it goes through this mechanism. Instead, there is simply a single concerted process which results in the change from starting materials to products. And where we've currently frozen the reaction is at the transition state of this process, where the bond between the nucleophile and substrate has only partially formed, and the bond between the remainder of the substrate and its leaving group has only partially broken. Now let's finish our reaction and see what happens. As this transition state follows down our energy diagram, we reach a point at which the leaving group has completely departed and the new nucleophile has attached itself to the substrate. And what's interesting about this mechanism is that this can only occur through the backside attack, which is to say that the nucleophile must attack from the opposing side of the substrate as the leaving group departs. Because of this feature of the mechanism, SN2 reactions will always proceed with complete inversion of stereochemistry. And so a chiral starting material should result in a chiral product in an SN2 reaction. Some factors that favor this particular mechanism include the presence of a strong nucleophile, as in this case hydroxide, which has a very local, dense negative charge and plenty of electron pairs which it's willing to donate to form bonds. Less substituted substrates also favor SN2. Recall that in this example we switched from a T-butyl halide to a methyl halide to demonstrate the SN2. This is because the formation of methyl cation is highly unlikely due to its low stability, and therefore the leaving group is more likely to remain attached to the substrate until the nucleophilic attack takes place. Additionally, poor leaving groups also favor the SN2 reaction, because the less likely the leaving group is to depart before nucleophilic attack, the more likely the SN2 mechanism is to take place. And finally, just as in the SN1 example, solvent choice can be very important, but will depend somewhat upon specific factors around whichever reaction it is that you're running. So always think about solvent choice, but always think so carefully in terms of the specific nucleophile, substrate, and leaving groups, and not just, well, an SN2 will always run by a certain or better in a certain type of solvent. So now that we have considered each of the two basic nucleophilic substitution reaction mechanisms individually, let's compare them side by side. Starting with the mechanism. The mechanism of an SN1 reaction is two steps. It involves first the departure of the leaving group, followed by the attack of the nucleophile. Whereas the SN2 reaction occurs in a single concerted step, in which the nucleophile attacks and the leaving group departs simultaneously. From a kinetics perspective, the SN1 follows first-order kinetics. Therefore, its rate law will be determined by only the concentration of the substrate, and the nucleophile does not enter into this equation. Whereas in the SN2 reaction, because the substrate and nucleophile are all reacting in a single step, both of their concentrations are considered. From a stereochemistry perspective, the SN1 reaction is expected to proceed with racemization of any chirality in the starting materials. Whereas in the case of the SN2, stereochemistry is inverted as a consequence of backside attack. As far as conditions which favor these two mechanisms, from the perspective of the nucleophile, the presence of a weak nucleophile will influence a reaction to run by the SN1 mechanism. This is because the nucleophile is less likely to attack before departure of the leaving group. As opposed to the SN2 mechanism, in which a strong nucleophile will favor this particular mechanism because it is more likely to attack before the departure of the leaving group. The identity of the substrate will also influence the mechanism. Highly substituted substrates, such as secondary, tertiary, or resonance stabilized species in which the carbocation is highly stabilized, will influence them to run by the SN1. Whereas the SN2 will run much more efficiently when less substituted species are used, such as methyls or primary alkyl halides. And finally, the identity of the leaving group. In the case of SN1 reactions, a good leaving group is favorable because it is more likely to depart and become the more stable leaving group species before the attack of the nucleophile. Whereas in the SN2 reaction, a poor leaving group is more desirable because this leaving group is more likely to stay on the substrate until the nucleophile attacks, initiating its departure. So this is a basic overview of the SN1 and SN2 reaction mechanisms.